Hope everyone had a wonderful weekend. Today's lecture is entitled, Why Is There a Heavy End? And any of you that have shown up for one of those moving parties with the Elders Quorum or the Relief Society, know that when you're moving a refrigerator, there's a smart end to grab and a not so smart end to grab, okay? Even though we're all, as Elder Uchtdorf suggested, we're all gonna lift where we stand. Some of us are lifting more than others. And that's what we're gonna talk about today is why is there that heavy end? And for those of you that have worked on cars, the short answer is torque, okay? Torque is what we're talking about today, okay? So we're gonna start with a little field trip. We don't often take field trips in this class, but today we're going to. We're gonna go out into a field that's covered with snow. And in that field is a frictionless pond of ice. And we're going to lay down on that frictionless pond of ice a meter stick, a standard meter stick. Now, if we push on that meter stick with 50 newtons to the right and 50 newtons to the left, we know by Newton's second law that that's going to give me a net force of 0. And that suggests that there should be no acceleration. And that feels fine. That's what our gut tells us is going to do. However, if I were to push here with 50 newtons and here with 50 newtons, Newton's second law still tells me that the net force is 0. When we drew our free body diagrams, we didn't care where the forces were applied. We just cared, is it left, is it right, is it up, is it down? And so this would still give me a net force of 0. And if you believe Newton's second law, as I taught it to you, that means that the acceleration of this meter stick is 0. Does that feel wrong or sick and wrong? Sick and wrong. Yeah, what's going to happen? Well, that thing's going to rotate. That thing's going to rotate. And folks, that can only mean one thing. That means Greg lied to you. Yeah, Greg lied to you. Okay, because you weren't ready for the truth. Okay, but now you are. Now, I'll have you note, there is one point on this meter stick that obeys Newton's second law. And what is it? Which point is not accelerating?
Center.
Yeah, the center. As that thing rotates, the center, we call it the center of mass, does not. It obeys Newton's second law. And indeed, that's the piece that you weren't ready for. I taught you this, okay? F net equals ma. But the truth is that F net is equal to the mass times the acceleration of a special point we call the center of mass. Now, when we deal with small objects like pebbles that we throw, everything's kind of moving the same. It's only when something is large and can have complicated motions about its center of mass that we have to worry about this distinction. And that's why in our problems so far, we've always used things that were relatively small and massive. Now, let me demonstrate this a little bit. Austin, I always pick on you, and I'm going to again. Get up here. You just look like you were a good missionary. Where'd you go? New Mexico. Okay, I need you over there and I need you to catch. Now, this thing has a floppy sort of motion to it. But if you concentrate on the orange ping pong ball, only look at the orange ping pong ball, just the orange ping pong ball. You're getting sleepy. Take out your wallet. Just concentrate on the orange ping pong ball. Back up a little bit, Austin. What you should see is that that orange ping pong ball travels in a perfect parabola, the projectile that's predicted by Newton's second law. Okay, now this is a little bit messier. Here we've got a really heavy ball that's filled with lead and a tennis ball. And we've arranged for this this orange ping pong ball to be movable. And so if I put it in the middle, that's obviously not the center of mass, okay? We haven't quite defined mathematically what the center of mass is, but you know it's not there in the middle because this is really heavy and this is really light. Now watch the orange ball. I hope no one gets hurt here. Oh, let's make it go higher. You can do better than I did. Oh, so glad the baby wasn't here today. That would have been bad. Now, we've made this so that the center of mass is there. You know, as you would imagine, it's closer to the heavy one there. And so now concentrate on the orange ball and see if it goes in a parabola. Did it? Say yes. Okay. Oh, and now we've broken it. Okay. You're going to pay for that, young lady. We spared no expense. Okay, your tuition. Oh no, you need to stay up here. Okay. Because I've got another one. This odd looking piece here has a flashlight right at the center of mass. And so what we're going to do is make, can you make that dark for me? I'm going to fling this over to Austin and you just follow the flashlight. Okay, send it on back. Oh yeah, you came real close to dying there, my lady. Okay, I think that's enough fun for today. Let's give him a hand, folks. We are going to have fun today, my friends. We are going to have fun today. Okay. Now, this is a picture of my third child, Christian, and he's performing a complicated maneuver off of that log, and his brother-in-law captured this picture. If we were to track his center of mass, which for a human his age is just a little bit behind the belly button, we would find that it would travel in a nice parabolic curve. My textbook, not the one that you're using, but the other textbook for the Physics for Poets class, in the 7th edition, I wanted to put this picture on the front cover. And I got a call from my publisher and he said, Greg, we can't use that picture. I said, well, why? So, that is one funny looking kid. There was a pause and I said, yeah, but he's my funny looking kid. And there was another pause and then he said, yeah, but funny looking's funny looking. So they put a picture that was of some athlete that anyway, that's what they wanted to go with. Now, let's talk about finding that center of mass. And we're going to use an analogy that you're all familiar with, your GPA. Now, my good friend Jeff Adams, he's from Canada. So I hacked into their higher education system and got his transcript. And you can see that he's good at physics, not so great at other things. Got 1 A and 4 C's. But he's got an A, he's got some C's, so the GPA's got to be like what? A B, 3.0? Does that feel right? No, that's not right at all. Okay, what we have to do, and this is what you do at the end of every semester, unless you have the computer do it for you, is you do a weighted average. What you do is you take each class and you have to weight it by how important that class is to your GPA. Okay, so this might be the grade that you got in physics, an A, and it's a 4-credit class. So you weight it by the 4 credits. This is the 2 you got in calculus, the C, and this is a 3-credit class. And then you add those up and you get 42, which seems like a high GPA, but remember this is Canada, so everything's kind of, you have to divide by the number of credits, by the weighting factors. And so when I divide by all those weighting factors, I get a GPA of 2.5. Now, I will tell you right now, that is not really Jeff Adams' transcript. He's one of the most brilliant people I know. And since I'm telling a story on him, I'll tell a story on me. I graduated from BYU in 1980. Can you imagine? That's when dinosaurs roamed the earth, okay? And I had done okay. I had really, really good grades and got into MIT. And when I got to MIT, I found that every country on the earth had sent their very smartest geeks to MIT. And I suddenly realized that I was at the bottom of the class. I was the kid that was struggling in every single class. Now in the grad school, in graduate level classes, everyone pretty much gets an A or a B. The top half of the class gets an A, the bottom half gets a B. Well, I was dead last. So I got a B in every single class. I got straight Bs. Well, my dad called at the end of the semester. He was so proud that his son had gone to MIT. He was just beside himself. He said, "How did it go, Greg?" I said, "Dad, I got a 4 point." He said, "That's wonderful. That's wonderful." I neglected to tell him that MIT was on a 5-point scale. That a 4-point meant straight Bs, and straight Bs meant bottom of the class. Well, that second semester, I got my feet under me. I figured things out. I got my family back to Boston with our new baby, and I was able to concentrate. And I got A's in all of my classes. So my dad called at the end of the second semester, "How did it go, Greg?" And I said, "I got straight A's." He said, "Just like last time." Dead silence. He never found out. He died a couple of years ago, so he knows now. And I'm going to have to face him someday. But while he was alive, he never found out. Okay. Now, we're going to be using this idea of center of mass with systems of mass. So if I had a beam that was all made out of the same material, say oak, and I wanted to know where the center of mass was, well, it's in the middle. That just speaks to our soul, does it not? And if I wanted to quantify that, I would set up a coordinate system. If I call the left end 0, I would say, well, that's at 2 meters if it's a 4-meter long board. But what if I added something to the system? What if I added this block that has 25 kilograms and I put it at x equals 3 meters? Well, that's going to move the center of mass. Is it going to move it to the left or to the right? Well, your gut tells you it's going to the right. but how far to the right? Well, to find that out, we do a weighted average. We take for each object, like the plank, the board, we take the position of the center of mass for the board, 2 meters, and we weight that by how important it is to the system. It makes up 50 kilograms. And then we take the center of the other object, the block, and we weight that by how important it is to the system. It represents 25 kilograms. And then we divide by the weighting factors, the total mass. And what we get when we divide that out is 2.33 meters. So the center of mass was moved to the right by 33 centimeters. I hope that just seems like old times, that you've been there before. That's boring, okay? The general equation, if you've got more than two things, is this here. You take each object, you take its center of mass times its mass, the second object, center of mass times its mass, keep on going, and then you divide by all the masses. You can do that in the x direction or the y direction, okay? And you're going to have to do that on your homework that's due this Friday. Okay, there's several problems, two indeed, that require you to find a center of mass. Are there questions on that concept of center of mass? When we were talking about two-dimensional collisions, remember we had that collision between the Volvo and the great big truck. We found that after the collision, they were moving at, well, 6.65 meters per second and an angle of 21 degrees north of east. We also said that the momentum of the system was the same before and after. Well, after the collision, we could see that momentum because they were stuck together. The truck, the Volvo, they were all moving in a direction 21 degrees north of east. But before the collision, there was nothing moving that direction. The Volvo was moving east, the truck was moving north of east by 37 degrees. Nothing was moving at 21 degrees north of east that we could see. But there was an invisible point, the center of mass, a mathematical computation that was moving at that speed in that direction, 6.65 meters per second at 21 degrees north of east, okay? So this becomes a powerful idea when we're talking about collisions in two dimensions. So let's talk about a new topic that we're gonna need, and that is stability. And you're probably amazed that someone like me is gonna talk about stability. Yeah. Have any of you been to the Leaning Tower of Pisa? Okay. Were they letting tourists go up in the tower when you went? No? Okay. I went when I was 8 years old. My family was living in Germany. We made a trip down to Italy, and I remember being terrified of that tower. And I was so grateful when I found out that that we were not going up in the tower. They were letting tourists go up in the tower, but my dad had 4 boys, and he was kind of cheap. And sorry, Dad. And he said we're not going up because I wasn't real thrilled about heights. Now, suppose that an entrepreneur came along and decided that we could fit more tourists in that tower if we just built it up higher. Well, why did it tip? If you add extra stories to a regular high rise, it doesn't tip over because all you're doing is moving the center of mass up. But with the Leaning Tower of Pisa, when you add extra stories, you're not only moving the center of mass up, you're moving it over. And as soon as that center of mass gets beyond the support, for reasons we'll talk about in about a half hour, it goes unstable. So that's our first big idea of stability. An object is stable when its center of mass is above the foundation. Now, you can earn money this way if you have friends that are non-members and that drink. If you go to pick them up at the bar, we only have one bar in Provo, and my brother used to be the bartender there. I'm sorry. We have stories about Kevin. But anyway, if you go and pick up your friend at 2 a.m, you can make money by challenging them to touch their toes while their heels are up against the wall. And no matter how they try, they can't do it, even if they're not drunk, okay? And the problem is that if your heels are up against the wall, as you lean forward, you're moving your center of mass forward. And as soon as that center of mass gets beyond your toes, you go unstable. Now, if I'm not up against the wall, I can touch my toes. And that's no small feat for someone my age, okay? Why can I? That is a pity clap. All of you, I'm dropping you a letter grade. Why can I do it out here? The caboose, okay? As I bend down, the caboose goes back, and that keeps my center of mass above my shoes, right? And I stay stable. Okay. Now, are any of you engaged to get married? Whoa, that's a lot of us. Okay. Have you met the in-laws yet? Oh, okay. Okay, well, next time you're at the in-laws, if you want to really impress them, what you want to do is take their good silverware, a fork and a spoon, and just ram them together so that they're never quite the same. And then take the toothpick that you were picking your teeth with and use that to balance this. On the edge of your glass. And then, to really impress them, oh, that really impresses them. Okay. My camera guy says I've got to move it over here. Okay. Let's give this another try.
Shut up. Just
This is a gray area because we know we're not supposed to have open flames in a chapel. And this is technically a classroom, but on Sunday it's also chapel. Judging by the fact that there's always a loaf of bread behind that counter on Monday. And so there you go. Were you able to see that in the back? Not so good? Okay. Let's do it again. Green Acres is the place for me. You don't even know that song. Okay.
light it on.
Oh, I just remembered I'm right-handed. Oh, you're going to have bruises all over after this lecture. So is there a chance this is gonna go wrong? Yeah, just did. I asked them to make the top less slippery,
What are we even?
but it looks like that did not happen. It keeps sliding.
Which is a bad one.
Okay. Let's make the top less slippery. You don't have any chewing gum, do you? Oh,
Yes.
keep slipping. Okay. Yeah. Let's use our imagination. When this works, this thing sits like that. Now, we said right up there that an object is stable when the center of mass is above its support. Well, the support is right here. And all of the mass, when it's sitting like this, is down here. Okay. What's going on? What's going on? Well, let's talk about that. I'm going to start with some pictures from the intertubes. You may have seen these pictures when they came by. This is a little car that went over the edge, probably at 2 a.m. from a late night at the pub. And as they're lifting it up out of the water, we get the center of mass out beyond the support, and there it goes over. Okay. So they bring in a bigger truck. You have a feeling what's going to happen, right? And sure enough, it goes over. This is a bad day. This is a bad day. Well, if we get that center of mass out beyond the support, we find that it seeks a point where the center of mass is directly below the support. So when I had the pitchfork and the shovel, I know that the center of mass of that system, it would be hard to calculate with math, but I know from this principle right here that it's got to be somewhere below this support right here. So it has to be somewhere along the pole. And we could figure out if we wanted to where that is. Now, this I'm going to demonstrate this. I normally would actually do this for real, but I had to leave my trained bear in Bozeman, Montana, so I just have a video of it. Look at that. I did it. I did it. Okay. So clearly either that little bear is very, very talented or else there's just no way he's gonna tip over. And you'll notice that he has those two little dowels, wooden dowels, and at the end of those dowels, there are lead weights. And that ensures that the center of mass of that system is approximately halfway between those lead weights, a little bit higher. But if Bobo tips one way, that center of mass is going to seek a location that's directly below the support, namely the string. And so if he tips to the right, that center of mass is going to try to get back underneath the string, and that's going to make him go upright. Now, have any of you been to the Boston Museum of Science in Seattle? No, the Boston one's not in Seattle. I meant the Seattle Museum of Science. You haven't. Okay, you have. Okay. They have this right here, and it's this great big track up in the sky, and they have an old Schwinn bike, and they've taken off the rubber wheels, so that you just have the metal rims, and that runs along this track. Now, you get to go all the way around this track, and the way it works, there's my dear wife, Sandra, and the way it works is that attached to this bike, there's this long rod that has big lead weights down below. And so if you tip one way, those weights are going to try to get underneath the track, and it will bring you back up. And you see that she's not concerned at all, but I am. I'm scared to death. Now, my children, this was my second time on this ride years later. When it was brand new, it was the big hot thing at the Science Museum. And my children guilted me into going on it. And when I finally got to the front of the line, I got halfway around and it tipped. And I froze. Like I said, I'm afraid of heights. And I just froze. And this kid, this 16-year-old that was running the ride, started talking to me. Sir, you're going to be okay. You're going to be, just push with your right foot. Now with your left foot. Push with your right foot now. And he got me slowly around while all of these people were watching me, and my kids were just going, oh, Dad. When I finally got around to the platform, this 16-year-old tried to explain the physics to me. I said, I understand the physics. I'm just scared spitless. Okay, I just scared spitless. So physics isn't always going to help you people. That's the message. Now, we have a new topic, the topic du jour, and I'm going to cover up the spring scale. I have two spring scales here, and they each measure force in newtons. And I have a bar, this bar here, that is 1 meter long, and it has a mass of 1 kilogram. I measured that before coming to class this morning. And I'm going to take another 1 kilogram, that's this one here, and I'm going to place it on the bar exactly halfway between the two spring scales. Okay. Now, tell your neighbor what the reading on the two spring scales are. Talk to your neighbor. Talk to Nimrod.
Oh yeah, no, the massive bars one. Then I don't know. They should be mass times the distance divided by all the distances.
Joshua, do you have any of that sticky tape that you use when you're wrapping up a bandage? Oh, man. How are you going to save anyone's life?
Yeah.
Okay.
Five. So the mass is 2.
Predict the reading on the scale. I hope everyone said it was going to be 10 newtons. Why? Because the total weight down is 20 newtons. And that means the total force up has to be 20 newtons. And the symmetry suggests there's no reason for one of those spring scales to be pulling harder than the other. And so sure enough, I've got 10 newtons on this one, and I've got 10 newtons, actually 9.8 if this, 10 newtons on this one. Okay, we spared no expense. It's got to be 10 newtons on each one. Now, that's where we've been. This is where we're going. If I move that over so that it is 80 centimeters from the left end, you know that one of these ends is going to be heavier than the other. Like when you go to that moving party. You know that this reading is going to be bigger than that reading. The question is, how much bigger? So with your clicker, tell me which of these it's going to be. Just let me get you started. Okay, now you can click.
Yeah, I guess.
That's on one side. I think it's those are the yeah. Is the thing one year? Yeah.
Okay. Last call. Get your vote in. Okay. Here we go. Whoa, we're all over the map. And I'm not going to tell you the answer, but I am going to tell you that A is not the answer. And so clearly, we have something to learn. Now, you'll notice that all of these options add up to 20. 4 and 16, 20, 5 and 15, 20, 6 and 14, 20, 7 and 13, 20, 8 and 12, 20. The old rules still apply. The center of mass of this system is not accelerating, so all the force up has to balance all the force down. I've got a total force down of 20 newtons. They have to be together pulling with 20 newtons, okay? But let's see if we can figure out which one it is. Now, we have to recognize that this idea of A equals 0 doesn't give us enough information. So we need a new idea. So let's go back to that frozen pond of ice in that field of snow. And let's put that meter stick back down. But this time, let's drill a hole right here at the bottom and drive a spike, like a golden spike in the promontory point. But this is going to be a frictionless point, pivot, a spike that's frictionless, so that this meter stick is forced to rotate about that point right there. Now, if I push with 50 newtons to the left and 50 newtons to the right, you know that both of those forces are the same size. But you also know that they're not going to have the same effect. That one of those is going to cause a greater rotation than the other. Okay, we call that torque. Both of those forces are 50 newtons, but they don't apply the same torque to the meter stick. And this is an idea that I hope that you're familiar with. If you're trying to get a nut off of a bolt that's frozen, and you're pulling on that wrench and it's not coming off. It's just really stuck. What do? You get a bigger wrench so that you can pull further away from the nut. Okay. And if that doesn't work, you get a post that you can put at the end of that great big wrench. And, you know, when you get far enough away, you eventually break that nut right off the bolt, and then you have to go back to Home Depot. Okay. Now, we say that F2 is creating a greater torque about this pivot point than F1. Now, so F2 is more effective in causing rotation, and this thing is going to rotate clockwise. Now, we saw there that how far away from the pivot is important. But what if I push with 50 newtons there and 50 newtons there? Okay, this one is being applied further away from the pivot, but your gut's telling you that this one's going to cause a rotation counterclockwise, and this one is not going to cause any rotation. Indeed, if you go up to a revolving door and you push like this directly towards the pivot, people are going to look at you funny. Okay, they're going to call security. Okay, now what we find here is that it depends on two things. This torque depends on two things: how far away from the pivot you're pushing and what angle you're pushing relative to that pivot. Okay, in general, what we do is we define a vector that goes from the pivot point to where the force is applied. Now, folks, that means that from now on, with these types of problems, we can't just draw the regular old free body diagram that we're used to. In the past, we always drew everything as a dot, whether it was a Greg or whether it was a cannonball, it was a dot representing the center of mass. But when we're talking about torque, where the force is applied and how it's applied matters. So we have to draw what we call an extended free body diagram, where we draw the object and we draw the force where it's applied on the object. And we define this position vector R going from the pivot point to where the force is applied. Now, the next thing we do is we define this angle. Listen carefully to my words, people. This angle is not between R and F. It's between the direction of R, which is towards the ceiling, and the direction of F, which is off this way. It's this angle here. Okay? Now, once we have that angle, we can define the torque as just the position vector magnitude, the force magnitude, times the sine of that angle between the direction of F and the direction of R. Now, the sine function is biggest. It can go from 0 to 1, but it's biggest when that angle is 90 degrees, right? And so that means I'm going to have the biggest rotating effect. I'm going to provide the biggest torque when I'm pushing perpendicular to that position vector, when this angle is 90 degrees. Okay? How are we doing? Tell your neighbor what a torque is. Okay?
Yeah. Understand it during
when we were talking about motion, we used R to represent position, just where something is. And so it's representing how far away from the pivot point the force is being applied.
Would there be a error? Yeah. Not talking about it.
I understand, like,
Okay, questions?
How so?
The R is the position vector. Remember when we were talking about kinematics motion? In 2 dimension, we used an R to represent where you were in town. And we broke that up into an X part and a Y part, but the position was R. Okay? Now, in practice, in 99% of all of your problems, in the homework, on the exam, you're going to be dealing with a force that is already perpendicular to that position vector, okay? And so in practice, 99% of the time, all you do is you take that force and multiply it by the distance to the pivot point. Because the angle between those two directions is 90 degrees and the sine of 90 degrees is 1. Okay, so in this case, I would just take the position vector of 3 meters times the force of 200 newtons, and I would say that the torque, the effectiveness causing rotation, is 600 meter newtons. Now, technically, I could also call that 600 Newton meters, but I never do. Because a Newton meter, Newton meter, Newton meter, Newton meter, what does that sound like? A joule, a joule. And this is very, very different, a very different concept than energy, okay? So I always call this meter newtons. And if we were in America, land of the free, what would we use? Mechanics? No mechanics. You got to be a bunch of foot pounds. Yeah, going to be a bunch of doctors, but no one wants to be a surgeon, huh? Who would work on cars. Okay, foot pounds. In this country, would be foot pounds. Now, again, 99% of the time, the force is already perpendicular to the position vector, and I just multiply them together. But what about that 1% of the time? What about that 1% of the time? Well, that's what we're going to be talking about in this week's tutorial. How do I deal with it when that angle is not 90 degrees? Okay, so if it's not 90 degrees, there's 2 methods that we can use. The first method I call the useful force method. And that is, I take that force and I break it up into its components. And if I think of these 2 blue arrows as 2 strings that are pulling, I put them in the shape of a triangle so that I could do some trig, but all the force is being applied right there. So this component is pulling to the left, and this component is pulling straight up towards the ceiling. Well, that means that this component here is not going to cause rotation. If you attach a rope there and pull straight up, it's not going to rotate this about that pivot point there, okay? So it's only this component that's giving me a torque. Now let's do some trig. This angle is going to be that angle by interior angles. And that means that this part of the force, this part that's perpendicular, is going to be F sine theta. And so if I look at my general definition, there's my F sine theta right there. And so you see what I get is just all of the position vector times the part of the force that's actually effective in causing rotation, the perpendicular part of the force. Okay? Does that make sense? Only part of that force is going to cause rotation. That's the part I want to use. That's the useful part. Now, the second way of doing it is just the opposite. What we do is we extend that force in both directions forever in what we call the line of action, the line along which that force is applied. And then we look for the distance from the pivot that is perpendicular to that line. Okay? Now, this angle is going to be equal to that angle. These two lines cross each other. And so this, if I see this triangle as that's the hypotenuse, that's the opposite side, there's the right angle right there. This is going to be this, we call it the lever arm, and it's just the position vector, the hypotenuse, times the sine of that angle there. And if I go back to that general definition, there's my r sine theta, there's my lever arm. Again, people, a torque is just a force times the distance to the pivot, but they got to be perpendicular to each other. And this force is perpendicular to this distance to the pivot. Okay, this force is equal to this distance, is perpendicular to this distance to the pivot. Now you see, we did the opposite in those two techniques. In the first technique, we used all of the position vector and only part of the force, the part that was perpendicular. In this second method, we use all of the force, but only part of the position vector, the part that's perpendicular. Now, Greg, why give me two techniques when I didn't even want one? I came into this room today not knowing that I needed this. Okay, I was getting through my life just fine. And then you give me two methods for something I don't care about. Well, it turns out on the exam and in your homework, there are going to be some problems where this method makes it trivial. You can see the answer. It jumps right out at you. But the other technique makes it messy. There are other problems where the useful force makes it obvious what the answer is. But this one makes it messy. In your tutorial, you're going to practice both of those, okay? Both of those. Check with your neighbor, see if your neighbor understands these two different methods. Okay. How we doing? Are there questions? Okay. In a nutshell, a net torque causes angular acceleration in much the same way that a net force causes linear acceleration. Okay, you remember angular acceleration is our alpha from last day. Okay. What we find is that the direction of this torque, this new idea, is given by a new right-hand rule. When you get to your exam, you will have two, count them, two right-hand rules in your toolbox. Well, how do we do this right-hand rule? Well, it turns out that torque is defined this way. You start with your right hand at the pivot point, and then you reach with your right hand out to where the force is applied. Now, this is the important part, people. This is the money step. You have to turn your wrist so that you can wave in the direction of the force. That's going to force your right thumb to be pointing in the direction of the torque. Now, folks, if you can draw both the position vector and the force on a flat piece of paper or on this screen, the only two possible directions for that torque are either out of the page or into the page, out of the screen or into the screen. So you don't have to be really, really gifted at this right-hand rule. You know whether your right hand's pointing out of the screen or into the screen, right? Okay. And you left-handed people, you get to work the problem while you're still answering the question. You win. You win. Okay? Now, if I started with that meter stick not moving, and if I always applied a force that was, I don't know, let's say 45 degrees relative to that position vector, what's going to happen is that this thing's going to start rotating. And if that force is always at that angle, it's going to speed up, speed up, speed up, speed up, speed up. By the first right-hand rule, remember that's the one where you curl your fingers in the direction of rotation. My omega vector, my angular velocity vector, is going to be out towards you. It's speeding up. So what direction would the alpha vector be? Same direction, out. And sure enough, the torque that's causing that alpha has to be in the same direction. If the torque is out of the page, the alpha would be out of the page. And again, you're going to practice that in this next tutorial. Okay, let's look again at our wheel of serious injury. Sam, would you do me a favor? Would you muscle that over out of the way so that I don't run into it? I've kind of botched a lot of things on this. Oh, and Sam, while you're back there, would you plug in my motor? It needs electricity. But we'll understand that next semester, folks. We'll study electricity. For now, just take my word for it.
I was saying it was like this way.
Sam, one more thing. Would you put that blue, put that on the middle stand there? No. Now, what direction is the omega vector, people, with right-hand rule number 1? It's out towards you, right? Now, if I hold it by this string, it precesses. Remember, the omega vector is pointing out that pole, and so that omega vector is changing direction. So there is an alpha, an angular acceleration, and it's going to be perpendicular to that omega vector. Now, I want you to get out your phones and take a picture right now. Oh, you didn't. Okay. Take a picture right now. Okay, you didn't again, so I'm going to take the picture. I'm going to take the picture right now. Okay, I just froze time. Okay, and I don't want to hold it there because I'm not strong enough. So let's suppose that we just froze time with your picture with me like that. Okay, what direction's the omega vector? Point with your finger, everyone. The omega vector, that way. What direction's the alpha vector, people? Point that way. No, you're not doing it. Okay. Remember, let me see if I can help you. The omega vector was out. In this case, it would be that way. And because this thing is changing direction, the alpha has to be perpendicular in the direction it's changing. And so since it was precessing around like this, the alpha vector is going to be away from you towards the screen. Does that make sense? See if your neighbor figured that out.
Always gonna be.
Right.
It's speeding up.
Okay. Sam brings up an important point. That's assuming that the spin rate's not slowing down, that all it's doing is changing the direction of the omega vector. Okay. And that's why I've put lead pieces around that wheel, is so that it doesn't want to slow down. And we'll talk about that on Thursday. Okay. Does everyone see why the alpha vector has to be pointing away from you towards the screen? Okay. Yes.
Still confused. Could you explain it one?
You're not seeing it?
Really?
Okay, so Sam, you're gonna be the alpha vector. Okay, let me get it spun up again. Okay. The omega vector is out this pole always, right? And the alpha vector is going to be pointing in the direction the omega vector is going. So why don't you stand over here, put your hand out, and I want you to always be perpendicular to that as it goes around, okay? And don't let it hit you, okay? Okay. I told you to take the picture there. What direction was his finger? I told you to take the picture there. What direction was his finger? Okay, now I'm going to take the picture there. Okay, and the alpha vector is away from you. Okay, that help?
The alpha vector is always going to be perpendicular to
To the omega vector.
It's going to be in the direction.
Yes. Was there another question?
You know why the wheel goes around the circle to the left?
Why does it go around?
Like to the left though, and not to the right.
I will. I'll do that right now. I'm going to do that right now.
So rotation is not a good.
Let's. Does anyone see my clicker?
I thought it was pointing out.
Is it possible that it's underneath this? Oh, no, it's on the side of it. Okay. Hey, look, people, it's still balanced. Your in-laws are going to be so impressed. They're going to get kicked right out of the family. Let's talk about the net torque. A moment ago, I said the net torque causes the alpha vector, the angular acceleration vector. If the net torque causes the alpha, it has to be in the same direction as the alpha. Now, we said that the omega vector, when it's in that position, is to your right, and the alpha vector is away from you towards the screen. Well, let's find the direction of the net torque using that new right-hand rule. Well, everything was rotating about this point right here. That's what it was precessing, we call it. It was precessing about that point right there. And if we draw an extended free body diagram, the first force I put on any diagram is the weight force. And folks, I always, every thinking time, put it at the center of mass. I'm going to tempt you sometime in the near future to put it elsewhere. Don't fall for it. Always at the center of mass. And since all the mass is with this lead in the middle, that's going to be right there. Right there. Now, the other force on this is the tension in the rope, and it goes along the rope. Now, if I use that as my pivot, because that's what everything's precessing about, and I ask, what direction is the torque that this force applies about that pivot? Well, remember, a torque is the force times the distance to the pivot. Well, the distance to the pivot is 0. Okay, that's like going up to the hinge of that door and pushing right at the hinge and expecting the door to open. Is it going to? No, no. So I get no torque due to this force here. Now, what about this weight force? Well, if I use that right-hand rule for torque, I start at the pivot, I reach out to where the force is applied. This is the important step. I turn my wrist so that I can wave in the direction of the force, and my thumb is in the direction of the torque. And so that torque is going to be into the page. To get the net torque, I add 0 to something in the page. And I get a total that's into the page. And that's why it goes around this way. If I had spun the wheel the other way, it would have precessed the other way. Okay? It would have precessed the other way. And I could actually make that happen. But to do that, I'd have to stop this, and that's going to hurt. Okay. So last time I spun it up this way. So let's turn it around. Okay. Now, that's the opposite of what it did before, right? Last time it was going around this way. Now it's going around that way. Now, if I make my torque smaller by making my position vector smaller, I will get a smaller torque and a smaller rotation. How do I do that? Oh, maybe with this. Let me see if I can. I didn't think this through. Okay, I've reduced the lever arm, and now it processes very slowly because my torque is much smaller because my position vector is smaller. Okay. Whereas if I hold it further out, it processes more quickly. I have a bigger torque, bigger angular acceleration. Okay, check with your neighbor, do a buddy check. Can't hold it much longer.
I think the position vector started the movement and where
Okay. If the net torque is 0, we get a constant omega. Just like if the net force is 0, we get a 0 acceleration and a constant velocity. Doubling, we find that doubling the net torque doubles the alpha, and so they are proportional to each other. We'll talk about that proportionality on Thursday. Now, this idea of torque explains our idea of the center of mass seeking a location directly below the support. If I have an odd-shaped object, this particular odd-shaped object, its center of mass is that hole right there. And if I move that center of mass away from directly below the support, it's going to seek a location where that center of mass is directly below. And the reason for that is that if I look at this situation on the left, the weight force acts at the center of mass towards the center of the earth. And if I draw my line of action, it goes right through my pivot. So I get no lever arm. If I do the same thing over here, by moving the center of mass to the right, I move the line of action to the right. And so now I have a lever arm. And that's going to cause a torque. That's this force times this lever arm. And that's going to swing it back around there. Okay. Now, folks, this is going to help you with your homework. So these 3 minutes are going to be useful. If I wanted to know how hard I'd have to pull right here to keep this beam from rotating, your gut tells you I would have to pull with 200 newtons. This 200 newtons would have to be balanced by that 200 newtons. But if I move that spring scale here, halfway down, it's 400 newtons. Let's see why. Well, in the olden days, if I had something in equilibrium, it had zero acceleration, I would know that all the force to the right has to be balanced by all the force to the left. If I had 100 and 150, this would have to be 250. Now, when I'm looking at torque, what I say is that since there's no angular acceleration, all the torque that's causing clockwise rotation has to balance all the clock that's doing counterclockwise torque rotation. So that means that this would have to be 800 newtons, because 200 times 1 meter distance to the pivot is equal to 800 times distance to the pivot 1/4 meter. That makes sense? The torque clockwise has to balance the torque counterclockwise. Okay? And that's going to allow us to solve this problem. We don't have time to do it today. On Thursday, we'll start class with that one. Thanks for your attendance. I know that this is a challenging topic. I know this is going to be a little bit of a stretch, but we'll do it. I have faith in you.